Good evening, everyone. Welcome to the week 8 NPTEL tutorial of Bioreactor Design and Analysis course. Um, so, this now we are going to solve some problems related to your scale-up and non-ideal reactors. So, I hope you have finished all your course content and submitted your assignments. Um, so, we'll wait for another 2 to 3 minutes and then start with the first problem. So let's start solving the problem. The question number 1 is related to the scale-up problem. So the optimum design parameters for cultivation of Saccharomyces filamentosus in 10-liter pilot plant was found to be following, which is the diameter of the impeller, which is di is given, which is 5 centimeter, and your height to this is your height to diameter ratio of which is given as 3. Your aeration is given as 1 volume uh, VVM. So the agitation speed is around 300 rpm. Now the process is to be scaled up to a 10,000 liter bioreactor. So you were asked to determine the scale-up ratio for the system. The question B is to determine the impeller diameter of the large bioreactor. C is to determine the agitator speed in rpm of the larger bioreactor if the scale-up criteria is based on constant Reynolds number. So the question D is to determine the agitator speed in terms of RPM of the larger bioreactor if the scale criteria is based on constant ungassed power output. And the question E is to determine the agitator speed in RPM of the large bioreactor if the scale criteria is based on constant tip speed. So I hope you remember the scale-up criteria based on this Reynolds number, constant ungassed power input, constant impeller tip speed, etc. If you remember those, we can easily solve this problem. So let's start solving the problem. First, we will write down the given first. So your volume of, let's denote the volume of smaller reactor as 10 liter, Vs, and your volume of the larger reactor is Vl, which is 10,000 liter. So what else is given? Your di is 5 centimeter and your h by d is 3. Radiation is how much? So radiation is 1 ppm and the agitation is 300 rpm. Okay, so let's start solving the problem. How do we, our first question is to find the scale-up ratio. So how do we calculate the scale-up ratio? So let's assume that our reactor is cylindrical in shape. So if you assume that, and if you assume that for scale up to happen, it should be dynamic and geometrical similarity should be there between the reactors. So if you consider that in mind, you can start by calculating using your volume of cylinder formula, which is what? Diameter of your impeller we have taken and height of the tank, which is your reactor. I hope you remember in scale-up criteria questions, like when the theory was taught, but your h by d is given as 3. So this is what this tank dia, right? Sorry. So if you take this into consideration, your h will be calculated as 3 into dt. So your volume equation will become volume is equal to pi by 4 di square, which is here, and instead of this d, you will be substituting 3 into dt. So this is the only. So if this comes into picture, how do you substitute this? It will become volume is equal to pi by 4 into 3 into tank diameter the whole cube. So if we substitute this, we will get your volume. So we already have the volume, right? What is asked here? What we have to find out? We have to find out your volume is already given, which is 10,000 liter. If you send, this can be converted to your centimeter cube, right? So you want this tank dia, which is not given. So keeping this in one side, into divided by your 3 pi. So dp v into 4, 3 pi, the whole power of 1 by 3. So if you do this, what we will get? The volume is 10,000 centimeter cube into 4 divided by 2.5, the power of 1 by 3. So if we do this, sorry. So what would be the answer we will get? Sorry. Um, Sorry. So we were solving for your dt. So what would be the answer of dt? Um, so sorry, I'm not aware of this negative marking thing. I have actually no clue about the exams. So please write to the concerned people, so they will get back to you with the correct reply for your question. I'm not aware of this. Sorry. So So your DT value will come around your 6.2 centimeter. So if your DT is around 6.2 centimeter, your H by D is how much? It is 3, right? So if you substitute it here, that your H will be calculated as 48.6, and how do we calculate your DI? How do we calculate your DI? So let me know how do we calculate DI. I will give you the answer, but you have to let me know how we have come to this. Okay. So our DI will be 4.9, or approximately we can take it 5. It's also already given, I guess. Correct, it's given. So, but you should be able to calculate it also with the given data. So if we consider these things, we can easily calculate our scalar factor. Your 10,000 liter reactor by your, what is your scalar factor actually? How do we calculate it? It is actually your cube root of your bigger tank by smaller tank, right? So this will give you 10. So your scale up ratio is 10. The answer for A is 10. What is the second question you were asked? You were asked about to determine the impeller diameter of the larger bioreactor. So how do we calculate the larger bioreactor dia? You guys have solved your assignments, right? So I think you will be able to answer the question. What you have to do, you have to, once you found out your scale up factor, you have to multiply it by your smaller scale reactors dimensions. So if you do so, the larger bioreactor would be, your DT of your larger bioreactor would be 6.2 into 10. If you do that, it is 162 centimeter, or you can keep as 1.62 meter. Similarly, your DI would be, it was given as 5 centimeter, right? So it will be 50 centimeter, correct? So 50 centimeter is 0.5 meter, right? So your height of the reactor is 48.6 centimeter, means it will be 4.86 meter. How much this would be? Point 86 meter. So you found the answer for your A and B. This is answer 10. This, what is the simple diameter? Is 0.5 meter. So you were asked to determine the agitator speed in terms of RPM. For the larger bioreactor, the scale-up criteria is based on constant Reynolds number. So how do you calculate your agitation speed in RPM based on the constant Reynolds number? I hope you remember this. So your Reynolds number is rho n d square by mu, right? So this should be constant for both your small and large reactor. So let's keep it as let S denote small reactor and L denote the larger reactor. Your mu will remain same, so we can cancel that, right? So rho n d square equal to rho n d square. This is your larger diameter L, and this L, and this L divided by, sorry, this is S. So these both will cancel, these will get cancelled. That is again ns ds square is equal to nl dl square. So this is how you get your constant Reynolds number criteria. So if you rearrange these things, you were asked to identify what the larger bioreactor's agitator speed, which is nl, right? So nl is equal to ns ds square divided by your dl square. So if you keep this and calculate things, what is the we will be able to get the answer for this. So what is the diameter of the we will calculate. Please substitute and calculate this. What is your diameter? What would be answer? would be around 3 rpm. Please solve it along with me. So your question D is about your scale-up criteria based on constant ungassed power input. How do you write that? Your constant power input ungassed. Then by P is equal to NP power number rho n q d power of I. This is liver tank diagram, right? So what are the constant things here? We can remove those things. So these two are constant. So n cube d power of I equal to n cube d power of I. So this is your S, L, L. So what do you want? You were asked about your NL. Q is equal to NS cube d power of I divided by DL 5 whole power of 3. If you do this, how does NL become like this? Your NS, these two will get cancelled, so NS will come out. So it will be d power of T DL. Yes, 5 by 3. So if you substitute this, your RPM for your smaller bioreactor is 300. So your DS, which is 16.2 centimeter, this is 162 centimeter, right? So cancel this 1 by 10, it will become 5 by 3. So if you substitute it, if you solve this equation, what is the answer? So it would be what 1 by 10.1 the whole power of 5 divided by 3. It's around 6.46. So if you use your design criteria as scale criteria as constant ungassed power input, then your impeller large scale reactors impeller sorry, the registration rate would be 6.46 rpm. So what is next question? It asked about determine the agitator speed in rpm of the larger bioreactor. The scale up criteria is based on constant impeller tip speed. So what is the criteria? How do we write that for constant impeller tip speed? So constant impeller tip speed is your NDI. Here make a note. This is diameter of the impeller is constant. So your NSDI DSI is equal to NLDLI. Write that. What would be the answer? Your NL is equal to NSDSI DLI. This given us 300 into 16.2 centimeter divided by 162 centimeter. Right. So it is 1 by 10. If you cancel it, will be 1 by 10. So it would be 30 rpm. So with these calculations, we complete the first question. We just found the scale up criteria, scale up ratio. Then we found the diameter of the larger bioreactor. Then we found the agitator speed of the larger bioreactor with the three different scale up criteria. So, so the next question is the plot which is shown below. Yeah.
Ma'am, I wanted to say something else, not related to this
Oh,
question. I wanted to say something about the assignments we had.
Okay.
Okay. I believe you are the research scholar under Professor Smithy, right?
I don't understand you. What?
Are you the research scholar under Professor Smithy?
Yeah.
Okay. Could you please tell her to reevaluate the week 7 assignment? She actually retrieved two questions because there was some mistake with the question. The only mistake was that the unit in which the answer is to be given was different, but the answers were correct. So
Okay. So have you
it
written it in the discussion forum?
no, haven't.
Uh,
Should I raise?
yeah, yeah, you should raise there because that is the only way you can communicate with the people responsible for your assignments and stuff related that. So
Oh,
thank you
okay.
for raising it here, but still you please post it in the discussion forum.
Yeah, okay.
Yeah. So if you have any doubts or clarifications, don't hesitate to post it in the discussion forum.
Okay.
Yeah. So the question number two is a plot is given below, which shows the concentration of the tracer with respect to time detected at the exit of the blood flow reactor after its pulse input. So the figure represents a reasonably good flow without any strong recirculation current. So is this statement about this graph is true or false? Sorry. So it's actually false. And we move to the next question. Sorry. Please take 2 minutes in reading the question and give me the answer. So determine the correctness or otherwise of the following assertion and reason. The assertion A is the bioreactor design parameter should be optimized to minimize any stagnant zones inside the reactor or dead zones you can call it. So the reason are the stagnant zones in the bioreactor can lower the mixing performance of the unit, thereby decreasing the efficiency of the bioprocess. So there are options given below. Take 2 minutes and then give me the answer. So the answer for this would be what? Both your assertion and the reason is correct, and your reason is the correct answer. Like your R is the correct reason for your assertion A. So the question number four, stimulus response experiment was carried out to understand the non-ideal conditions in a fungal bioreactor system of 1,000 liter. The following results were obtained. So if a E curve represents the exit age distribution, then for the system, sorry, this is 0 to infinity. EDT is 0 to infinity is what? So please look into the question and give me the answer. So this is a what curve it is. So you're asked about what would be this. So actually what would be the explanation is under your non-ideal conditions, the fluid elements will take different routes, right? So they thereby they will take different lengths of time when they pass through the vessel. So I hope you remember this residence time distribution of the fluid. So what is that? It is the distribution of the times for the stream of the fluid leaving the vessel, and which is called also called as exit age distribution E, or the resident time distribution. So actually the RTD is represented in such a way that the area under the curve is unity, means your uh, 0 to infinity E dt is always given as 1. So the answer would be 1. So a problem which comes with non-ideal conditions. So the question 5 is, a batch of the radioactive material is dumped into a river, and at a dam about 400 km downstream, the flowing waters are monitored for a particular radioisotope, and the date of the following figures are obtained. So this is a graph which gives you concentration of which is the units of radioactivity per meter cube with respect to time. So you were asked the area under the curve in terms of units of radioactivity into days per meter cube under the C curve. And the second question is, how many units of this tracer, which is the radioactive isotope, were introduced into the river? So you had a similar assignment problem, I guess. So I think you guys will help me in solving these questions. You know that I already, right? So start with, can anyone of you start with how do we have to start this problem? So you were given the units, so that would be easily easy for you to calculate. So flow rate is already given, right? So how do we calculate the area under the curve? So base, your base is what? 125 minus 20 is your base, and your height is 10 power of minus 6. So it will out it would be minus 6. The unit here is radioactivity per meter cube, right? So this would be days. So radioactivity into days divided by meter cube. So this would be the answer for your first question. So what is the second question? How many units of the tracer? That is only the radioactivity unit. If you have any doubts, you just note down the units. Based on that, you can easily calculate. So how many unit of the tracer, which is the radioisotope, is being introduced into the river? So to calculate that, what you will do? So you know the answer of your area under the curve. So area under the curve is what? Equal to your units of, that is radioactivity into days per meter cube, right? Yeah. So unit of traces, the unit will be radioactivity and your flow rate. For this, the unit will be what? Meter cube per second it is given. We will convert it to hours. So if you do that, you know the area under the curve. Let's keep it here. So this side will be 52.5 into 10 power minus 6, and unit of the tracer you need, and flow rate should be in terms of days because the unit then only will get cancelled. That is the case. This is per second, right? We should convert it into minutes. So what would be the answer? It would be 52.106 into your flow rate to 24 hours. So this would be the answer for this question. Sorry. Um, we'll start in 2 to 3 minutes. Please read this question. It is about the scalar. So the last question, I got confused for the life. So I'll rewrite it again. So the how many units of the trace radioactivity were introduced into the river? We just found that the area of the radioactivity per meter cube is around 52.5 into 10 power of minus 6, right? So the unit will be the units radioactivity dot base per meter cube. So from this we can actually calculate this. How? You know the area under the curve. The unit is what? This radioactivity into your days divided by meter cube, right? And to get the same, we will call unit of tracer. The unit will be what? Radioactivity. And if you divide it by your flow rate, meter cube per second. So we can convert it into days because we have it in form of days. If you do this, we will get this value. So that's what we are going to do, but with the conversion factor. So 52.5 into 10 power of minus 6 radioactivity into days divided by meter cube into your flow rate is what? 6000 meter cube per second. This will get cancelled. Instead of seconds, how do you convert it into days? 60 into 60 into 4 seconds, 4 minutes, and your 24. If you do that, your answer will be so the answer would be what? 52.5 into 10 power of minus 6 into 518.4, which would be 27216 radioactivity. Okay, sorry for the trouble. So the next question is your question number 6. So for question number 6, after the batch fermentation, the system is dismantled and approximately 75% of the cell mass is suspended in the liquid phase, which is 2 liters, while the 25% is attached to the reactor walls and internals in a thick film. So the work with radioactive traces, which show that 50% of the target product, which is intracellular, is associated with the cell fraction, and the productivity of the reactor is 2 gram of your product per liter at the 2 liter scale. So what would be the productivity at 20,000 liter scale if both the reactors had a height to diameter ratio of 2 is to 1, like 2 to 1, which is your H by D is 2, right? So how do we, what is asked in this question and how do we start solving this? So you were given a productivity for your small scale reactor and you were asked the productivity for a larger scale. So first you have to find out the dimensions of your large scale reactor, then we can proceed with your uh, productivity calculations. So how do we start with that? So the volume of the reactor would be 5 by 4 d square into h. So from your h by d, h is equal to 2d. So if you do that, it is 5 by 4 d square into 2d. That would be pi by 2 d cube, correct? So what would be the diameter of the system? How do we calculate this? We'll call the system as S only. This is what can be pi d into h. We know your pi d into 2d, 44 pi d squared. So for a 2-liter system, the diameter is what? How do we calculate this? The volume is given now. From this we can calculate this, right? Volume is 2 liter for a 2-liter system. So pi by 2 dq volume by 2.17 power of 180. Centimeter cube. So 1 meter is 10 to the power 3 centimeter cube. So that is the case. How it will become 2 into 10 to the power 3. Let's see. 10.8 centimeter. So your D value will be 10.8 centimeter. So S would be pi d, pi into 2 pi d square, right? So it would have become 2 into 3.4 into 10.8 whole square. what it would become. So this will become as 10.8 the whole square. 2 over 2 into 3.15. It's around 732.49 centimeters. And what else you need? I need the, you know, the volume already. So for a 20,000 liter system, how do we calculate? You have to calculate it. What is the scale up factor? 20,000 divided by 2 liter, right? The whole power of 1 by 3. 1000 by 3 is 10. So your scale up criteria is again 10. Ten thousand liter, right? Criteria is around 21.54. So if you multiply the scale up criteria with your um, diameter of the small reactor and then AS of the small reactor, then you will be able to get the values for the larger reactor. So if you do so, diameter of the larger reactor will become 21.54 into 10.8 centimeters. This will become 21.54 into 10.8. 232.6, right? That's 232.6 centimeter. Yours will be 21.54 into 738 centimeters square. That's 138. And your volume is 20,000 liters, right? Twenty into 20,000 centimeters. your D was around 232.6, right, centimeter. So D is around 232.6 centimeter. You will also repeat it by D square. 2 into 3.14 into 232.6 the whole square. So we are around 342, 342 1.73 centimeters square. And the volume of the larger reactor will be 2 into 10 to the power 7 centimeter cube. So, the amount of for the one dense scale reactor, for 2-liter reactor, amount of the product made by your surface attached cell is amount of product by surface attached cell is your productivity 2 gram per liter into your 2 liter. How much is means for your 738 centimeter square of surface area. So for to calculate similarly for the amount of product formed at your 20,000 liter reactor due to surface attached growth is what it would be your how much is your surface area 30 how much did we calculate sorry 34 34 2399 34 divided by 738 centimeter square. This is 2 gram for 738 into 2 gram. If you do this, what would be the answer? It is around 27 grams. So for a 2-liter system yield is 2 gram per liter into your 2 gram. Okay, your 2 liter, right? 2 liter reactor. So it was 2 gram. So the overall yield in your 20,000 liter reactor is how much? This one, this is 927 grams due to attachment plus 2 gram per liter is the productivity of the other reactor, 50% right? 50 into volume is 20,000. Equal to what is the answer? This is somewhere around 20,928 grams. This is the concentration actually. So if there is no, like sorry, the amount. So if there is no wall growth is present, the 20,000 reactor would have yielded more. So if there is wall growth in your scaled up reactor, that is going to significantly impact your productivity. So I hope you understood the previous problem, and let's start solving the question number 7. So please take few minutes to read the problem. I'll also read. So consider the scale up of a fermentation from 10 meter to 10,000 meter vessels. The smaller fermenter has a high Q diameter ratio of 3 and the impeller diameter is 30% of the tank dia. So the excitation speed is 500 rpm and 3 Russian impellers are used. You are asked to determine the dimensions of the large fermenter and agitator speed. For a constant P by V, a constant impeller tip speed has a height to diameter ratio of 3, and you are again given the impeller dia, which is 30% of the tank dia, and using constant Reynolds number. Sorry. Please take few minutes to read the question. We'll start solving in another 2 minutes. So you start by writing down the given values. Your small scale fermentation uses the volume of the small reactor is 10 liter and the large scale reactor is 10,000 liter. What would be the scale up ratio? This is 10,000 divided by 10. You do this, so your scale up ratio is 10, and your H by D for your small reactor is 3, means your H is equal to 3D. And you were also told that the impeller this Di is 30% of dt, which is 0.3 dt. D, Di is equal to zero point 0.3 into dt. So what else is given? The agitation is 500 rpm. So you were asked to calculate what? You were asked to calculate the dimensions of the larger fermenter and the agitator speed by using your data criteria. For example, your question A is constant P by V, question B is your constant impeller tip speed, and question C is your constant Reynolds number. This is very similar to your first problem which we solved. So you can solve it on your own, but we will take a few minutes to read the question and start solving. So how do we start? So if you assume, so assuming geometric similarity in both the reactors. The volume of cylinder will be divided by cylindrical reactor. Okay. Uh, so we know from there the H is equal to 3D. So if you substitute this 5 by 4 dt cube into 3. So volume was 10,000 liter. This we can, so 1 liter is equal to 10 power 3 centimeter cube, right? So if you rearrange things, L cube T cube is equal to 4 divided by 3 into 3.14. Cancel 4 into 10 to the power 4. So with this what you will get? This is 16.19. Keep it as 16.2 centimeter. Okay. So we got your tank diameter as 16.2 centimeter, and your, how do we calculate your impeller dia? It is given as 0.3 into D, which is dt is 0.3 into 16.2. Two point nine centimeter. Your height, how do we calculate? H by D is equal to how much it is? H by D is given as 3, right? Given as 3, right? So you just found your DT value. So H is equal to 3 into 16.2, which will be 48.6 centimeter. So you just now have calculated all your dimensions. Scale factor also you know. So for the large scale reactor, the diameter would be 16.2 centimeter into 10. Without that, it is 162 centimeter or 1.62 meter. And what would be the diameter of the impeller? It would be 4.9 centimeter into 10, which would be 49 centimeter. This is 0.49 meter. And your height will be 48.6 centimeter into 10, which will be equal to 4.86 meter. So this is the dimensions of your large scale bioreactor. So what was asked? It was asked to calculate the dimensions and the agitator speed based on your constant in P by V, constant impeller tip speed and constant Reynolds number. So for the constant P by V, how do we calculate? So in case of constant P by V, we have to keep your n cube dt squared as constant. Here also you were asked about your larger bioreactor, right? So for the in case of larger bioreactor, your NL cube is equal to NS cube dt square divided by dt square of your larger bioreactor. Sorry. So NL is equal to NS cube square divided by dt whole power of 1 by 3. So that it will be actually NS T divided by DLT the whole power of 2 by 3. So what is your small scale reactor's agitation, which is 500 rpm, and this is actually 16.2 divided by 162 centimeter, 1 by 10, right? So what would be the answer? The answer of your large scale reactor's agitation rate is, what is the answer? Sorry. The answer would be 107 rpm. So similarly, if you do for the constant tip speed, so for the constant tip speed, it is what? NPT, right? Yes. Is TST divided by TLT. So your S is 500. Tank dia is what? How much? The small scale is 16.2, that is 162, right? 16.2 divided by 1 by 10. So the answer would be 500 into 1 by 10, which is 50 rpm. So based on your constant tip speed, the agitation will be 50 rpm. So what is the question C? We are asked for constant Reynolds number, right? So in case of constant Reynolds number, how do you do? This is for L, this is for small reactor. But these will be constant, so we can cancel. Then it will be equal to N dt square is equal to NL dt square. This is your small, and this is your large. So your NL would be Ns to do the write it here. NL is equal to your Ns is 500 into Ts is 1 by 10 the whole square. If you do this, the answer would be 5 rpm. So in case of this, the rpm is 107 rpm. In case of this, it is 50 rpm. In case of this, it is 5 rpm. This and all is negligible. We cannot do like this. So how do you conclude the from observing the results? What do you? How can you give a select the criteria which you will be using for your scale-up basis? So we can use the scale-up based on the constant P by V, which will be the most likely choice. Uh, but if your cells being used as shear sensitive, we cannot consider that. So your constant Reynolds number based scalar criteria will yield you a RPM of 5 RPM, which cannot be considered actually. It is very low. So you can either go with your constant P by V if in case your cells are uh, not shear sensitive. Otherwise, you can go with 50 RPM if they are shear sensitive. Sorry. So we have the last question, which is a very simple basic question. So you were given a concentration ratings as a continuous response to a pulse time, pulse input into a closed vessel, which is to be used as a chemical reactor. So they're asked to calculate the mean resident time of fluid in the vessel T and to tabulate and plot the exit age distribution E. So how do you draw the E curve? How can you draw it actually? So it is basically it's a very simple problem. So we'll start solving it. So how by looking into the table, can anyone of you let me know how to calculate the mean residence time and what is mean residence time? Hope you remember things. Okay. So we'll start solving the problem. So you were asked you to calculate the mean residence time of the fluid in the vessel T, and you were asked to tabulate and give a graph of the exit age distribution E. So how do we calculate the mean residence time? Mean residence time can be summation of your time, your concentration, and your time interval divided by summation of your concentration and your time interval. So your time interval is constant. So if you do so, this will be summation of your time and your concentration I and your summation of concentration I. Or this your so in this the time interval is given as del t, right? So the del t is 5 because the interval between these two are 5 minutes. So let's keep your del t as 5 minutes. So this is nothing but your summation of your concentration, and this is your summation of your time actually. So the area under the curve, how do you calculate summation del t is 3 plus 5 plus 5 plus 4 plus 2 plus 1. 3 plus 5 plus 5 plus 4 plus 2 plus 1 into your del t, which is 5. If you do that, it will be answer is 20 into 5, right? So that's 100. What is the unit? Gram per liter into minute. Gram per liter into minute. So this area will give you the total amount of tracer which is introduced inside the vessel. So to find the E value, the area under the curve must be given as unity, right? So from that we can see is to divide your concentration by your area, that will give you a age distribution. Please go through the lectures if you have forgotten these terms. So you have to calculate for individual concentration what is the E value. So if you do so, we'll make a table. So let's keep it as E, C by area. Okay, what is the concentration of 0 is 0 only. For 5, what is the concentration? It is 3. So for example, 3 divided by your area is what? Area is 100, right? Area is 100. Equal to 5 divided by 100, it is 0.05. Similarly, if you fill this tables here, 0.04, this will be 0.02, 0.01. So you just got a, you just were asked to plot, right? You were asked to tabulate and plot the exit age distribution. You just found the exit age distribution E, and from this, if you have a graph sheet, you can plot time in minutes. This will be this value and your E here. So E will be here. If you go to stable area. If you plot this, you will get a curve like this. This is your E curve. So I hope you have understood and get a better picture of the problem. So if you have any doubts, please mail in the discussion forum mentioning the date of the live session. So this would be the last live session. All the best for your exams. Uh, Thank you for joining the NPTEL Bioreactor Design Analysis tutorial session every week Fridays. So if you have any doubts, please put up a request in the discussion forum mentioning the date of the live session. Thank you.